Hello viewers and welcome to another episode of Space Science with Python. Now in the last couple of weeks it was a little bit quiet on this channel regarding coding and so on. I was a little bit on a short summer break, so yeah, I just threw in some small science video in between and now I'm back and I would say we can continue with our near-Earth object science project. And just to have a small recap what we want to do, so we want to get all the near-Earth object data we currently know and also simulated data and see how they appear in the night sky, what kind of telescope settings do we have to really identify even the smallest asteroids and so on and so forth. So it's really about the, let's say, this discoverability or the detectability of these objects, because these objects, well, they approach our Earth quite close, so it's really important to know where they are, where they come from, and also to know how to detect them. And today, well, in the last sessions we obtained the data, we took a look at the orbital elements and so on, and today we are going to compute the apparent magnitude, so the brightness of an object in night sky. So this will be the fundament for our future considerations, where we will compute the brightness distribution of all objects and then also put it on the sky map and so on. But today we will just pick one particular object and write the function of this apparent magnitude computation algorithm and see if it works. Now for our today's session, I choose an object. It's 433 Eros. And it's currently, well, not really visible. So you see here in this program called Stellarium that it's really close to the sun. So we can compute the apparent magnitude. You see it here. It's currently 12.64. And just a small recap, the larger the number, the fainter the object. So do not forget that. And, well, a value of 0 is the brightness of the star Vega. And you see also that the magnitude is actually a little bit reduced, so 12.8, because of, we have air mass between the observer and the object, and of course the atmospheric attenuation causes a reduced magnitude or a reduced brightness. Of course, this is really observational, observer location dependent, so now I choose here the current position here in Stuttgart, Germany, southern Germany. If I would choose now, I don't know, Greenland or the US or whatsoever, not any place in the US, but let's say New York or Los Angeles, this value would, of course, change. But we would like to compute the, let's say, atmospheric less or, the brightness, assuming that we do not have any atmospheric effects. And now, before we start, I would say we have to find a suitable date and time window where we could also observe it in the night sky. And I prepared something. I just increase the date time by a year, and then we go here to midnight. Now this is the ground, you see. We are tracking the object, and now we are around midnight, let's say. So let's write a 0 here. And we see it's above the horizon. It's in the middle of the night. And we see the object somewhere here, 433 Eros, with a magnitude of 11.24. So let's compute this value, or let's see how we can compute this, and also let's verify the function also for other dates. And before we do this, I would say we go a little bit into the theory. And this is a very comprehensive small script, or not a paper, but an article, 2 pages, about the Hg magnitude system for asteroids. And the Hg magnitude system for asteroids is an empirical equation that helps us to compute the apparent magnitude of, minor bodies, or let's say here asteroids. So the thing, it does not apply for comets, because comets are active, and there are also other equations for this. Now let's see. How is it defined? Well, we want to compute the apparent visual magnitude V. And there are a lot of equations here. We are not going too much into detail, but it's important to obtain the most important functions, like here the so-called reduced magnitude, H alpha, where we have the apparent magnitude, and we have to move this part to the left side, so to compute the visual apparent magnitude v, we have to compute the reduced magnitude plus 5 times the log of the distance of the asteroid from the sun times the distance from the asteroid from the Earth. So, and the reduced magnitude itself is defined here. It's linked with the so-called absolute magnitude of the asteroid, and if you recall one of the previous videos, the absolute magnitude is linked to the size of the object. And here we have a, let's say, a equation with a lot of trigonometric functions. Yeah, you have here the tangents. We have here also some kind of exponential function. Okay, it's not trigonometric function, but still, with a lot of different functions linked with each other, let's say, entangled in a way, and also some kind of constants. And again, this is an empirical equation, right? So there is no, I would say, it's not derived from any underlying theory. It's also important to mention that this equation is also valid for a certain frame, for a certain domain of so-called phase angles. So it's valid between, not greater 120 degrees. So what is the phase angle? Now imagine the object, so the asteroid, and you have also now the Earth and the Sun. And now imagine the vector from the asteroid to the Earth and to the Sun. And the angle between the vectors is the phase angle. And the phase angle should not be larger than 120 degrees. And what does it mean? For example, 180 degrees? Well, in this case, it's the object is in a straight line between the Sun and the Earth. And, well, it's kind of difficult to observe these kind of objects. So this is the lack of observational data leads to an empirical equation that it's only valid in a certain domain. Now, there's also another thing, like, for example, the slope parameter g. It's written here, it relates to the opposition effect and so on. We will not get much into detail what is the opposition effect. We will describe this in our next video to see how this equation behaves. And I would say, well, we have this value in our database, we just extract them and apply it. So what we have to do is we have to write functions that consider all these things that are described here in the small paper. Now I would say let's move to our script. And our script is, well, again, uploaded in the GitHub repository. So you know here the GitHub repository, it's under project near Earth objects, and then this is here script number 5. And I would say let's go a little bit through the script. So we want to compute the apparent magnitude of asteroids. In our very first cell, we are importing the standard libraries. I would also suggest to maybe restart the kernel, so to go here step by step. Now, importing everything, and here in cell number 2, we define the apparent magnitude functions. And well, I've wrote down now 3 functions. The apparent magnitude is here in the very last function, so the hg function, hg apparent magnitude, which requires the absolute magnitude, the vector from the object to the observer, and the vector from the object to the illumination source. I didn't call it sun, just illumination source. And well, in our case, it's always the sun. And of course, the slope parameter g with a default value of 0.15. So if we do not have any slope parameter value, we can assume a certain default value. Also some kind of, some descriptions and so on. And the function here simply takes the vectors, computes the distance or the length of these vectors, and then we are computing the phase angle between the vectors, and then we compute the reduced magnitude, so this h alpha you have seen, and this reduced magnitude function is defined here, reduced mag, where we put here the equation that's written here. And then we have also the other functions here with phi and so on. And this is also put here into another function. I call it just phase function, and it's being computed there. So I just separated in 3 scripts, functions. So if you would like to take a closer look at the functions, how they behave, just feel free to use them. You could also theoretically put everything into one function and work with it, but I just split it up into 3 parts. So this is now computing the apparent magnitude. Now, what do we need now for the apparent magnitude? Well, we need the state vector of the Earth for a particular date, and we need the state vector of our object. Not really the state vector, but the positional vector with respect to the Sun, so in heliocentric coordinates. In our case, first we need, of course, our SPICE functions. If you recall it, it's the SPICE functions that load the leap second kernel as well as the positional information of the planets. We need also to define the g time m value, so the heliocentric gravitational constant for the Sun. This will be used for a SPICE function, and also the definition of 1 astronomical unit in kilometers. We will use this also in a second. And then, of course, we need to assess our database, and then we extract our data for 433 Eros. And we simply use pandas with the function read SQL query, where we say, okay, select everything from the main table where the name equals 433. And then we provide the connector, so we can simply execute it. And here in the cell number 6, we see now the data, the information for Eros 433, like the name, the semi-major axis, eccentricity, inclination in degrees, also here the absolute magnitude, we will use this, or we will need this, as well as the slope parameter g, and here it's not 0.15, that's the default value, it's 0.46. Now, cool, let's go a little bit further, and in cell number 7 and 8, we are now computing the state vector. So we use the UTC time string I just showed you in Stellarium. We use the 14th of August in a year, so 2023. And we compute first the ephemeris time, and then we compute the vector from the Sun to the Earth with the function spk GPS. And then we are computing the positional vector of Eros with respect to the Sun using the function conics. And well, we have the modified Julian date in our database. We need the Julian date, and we can simply convert it by adding this value here. So it's simply a constant that is being used to switch between JD and MJD. And now the conics function requires the perihelion in kilometers, so we have to convert it, the eccentricity, then the inclination longitude of ascending node, argument of periapsis, and the mean anomaly, but given in radians, so we have to convert it. And then also the corresponding, so the orbital elements corresponding epoch in ephemeris time, which is now here, as well as the gravitational constant g times m for the Sun, and then also the ephemeris time for the time we would like to compute the state vector. So in our case, again, the 14th of August 2023. Now this is what we do in cell number 7. And well, now we have to convert the vectors a little bit. That's not magic or something, because we defined the function in a way that we need the vectors from the object to the Sun and from the object to the Earth. So we have to simply invert the function. The vector Eros to Sun is simply our vector we just computed, but inverted. So that's quite simple. And to compute the vector from Earth, from our object to Earth, we have simply to use now the vector. So this vector is object to Sun plus the vector from Sun to the Earth. So that's what we computed here in cell number 7. So we execute this, and now we are good to go to compute the apparent magnitude of 433 Eros at this particular time. So we call our function we just created with the absolute magnitude, vector object to observer, object to illumination source, in our case the Sun, and also the slope parameter g. Now it's very important to note that the function is defined, so absolute magnitude has no dimensionality as well as the slope parameter, but the vectors have to be given in AU. So we have to convert this kilometer-based vector back into AU. And this is now what we can do. We execute now cell number 9 and cell number 10. You already see it. We can now compute the apparent magnitude of Eros for this particular timestamp. And then we use the value and round it by 2 values, because this is also the value that Stellarium is giving us. So we have here now an apparent magnitude of 11.71. And I would suggest to compare this value now with Stellarium. Of course, Stellarium is, let's say, also not a ground truth. Also, there are a lot of different tools that provide values, but we can take a look now. And what did we compute? 11.71. And here it says 11.24. Now, let's see, where does the difference come from? We have an absolute magnitude of 10.4, and we have 10.87, so this could be the difference. So we could, for example, change here to the value that Stellarium is providing, 10.4. So let's see, 10.4. And now you see the object becomes a little bit brighter. It's now 11.24, and 11.24, it's the same value that Stellarium is giving us. So yeah, we should use our official values, and I will not store this one now in a GitHub repository, but just be aware that if your values differ a little bit from Stellarium or other tools, just always check the constants that are being provided. So the slope parameter appears to be the same. And I also checked some other date times, so where the object is a little bit brighter. So let's go 2 years in the future. And then I think it was November. And wow, it's quite beautiful now here with the Andromeda Galaxy. So let's move it a little bit to have a nice picture. So yeah, you can plan it. Yeah, tracking Eros at the end of November in 3 years. It's a really nice picture, I have to say. And we have now a magnitude of 9.93. So let's go back here and change the date. So 25, 11, and I think it was 30, right? Yeah. So we can recompute this, invert the, or change the vectors. We stay with the absolute magnitude of 10.4, and let's compute it. And we have here 9.99. Yeah, okay, we have a small difference. So yeah, maybe it's also based on rounding errors or something, or maybe after all the slope parameter is also a little bit different. Could also be. I think there is no slope parameter provided in this tool. Yeah, but that's fine. But you see that we are now able to compute the apparent magnitude of asteroids. So this function does not only apply for NEOs, but also for asteroids. And I think this is quite nice to have. And well, I will outsource these functions a little bit into some kind of auxiliary folder with some functions, because next time I would like to dive a little bit deeper into this apparent magnitude functionality to show you some effects and how, to show you the apparent magnitude curve, shape, and how it behaves and so on. So a little bit going into detail, and we will also talk about certain effects like the so-called opposition effect. Maybe I will do also a science video out of it. I don't know, maybe a mixture of both. So yeah, you have now a tool to compute the apparent magnitude, so the brightness of an asteroid or an NEO in the night sky. And I hope you learned something today and you still enjoy coding. And until next time, see you.